Extreme IO uses a system known as XDP, Extreme IO Data Protection, for storage resiliency. It is much more efficient and more powerful than traditional RAID. RAID has done a great job, but due to sizes of drives and the sizes of systems, it's starting to really have scaling problems. It takes too long to rebuild, takes too long to create volumes. It's too much overhead when we want to do writes. So a new system was created. And the nice thing here is it's only 8% overhead. If you go look at a common RAID 5 set, which would be like 5 drives in RAID 5, you immediately lose 20%. Or like an 8 drive RAID 6 set, same thing, you're going to lose like 25%. So it's much more efficient than that. There's no RAID levels, there's no stripe sizes, there's no tuning. It is just on and you don't worry about it. You don't have to figure out, do I need to put this on RAID 10, RAID 5, RAID 6. It's all handled. XDP does everything that you need. It also has very fast rebuild time. So we have a 10 terabyte brick sitting in the Vera lab here, and I've pulled drives and had them rebuild, and my time is 14 minutes for a 400 gig SSD. Now, your time may vary depending on the amount of I/O load you're putting on it, but I think 14 minutes across 25 drives is very, very reasonable. Actually, it's very, very good. So I think that just shows the potential of XDP. You can fail up to 5 drives in a single DAE or brick. Now, that doesn't mean you can walk up and pull 5 drives at one time. You do that, and bad things are going to happen. What it means is that you can walk up, pull 1 drive, let it rebuild, pull a second, let it rebuild, etc., up to 5. Does not mean 5 at once. 2 failures are calculated in the original overhead. So if you remember, on a 10 terabyte raw brick, you get 7.5 terabyte usable. Part of that space that you lose due to formatting and other stuff is also the 8% overhead that is calculated as 2 drives in the failure. So you're guaranteed to be able to walk up and pull a drive, rebuild, pull a second drive, and rebuild. To go for 3, 4, and 5, you need free capacity. So if you're at 95% utilization on your cluster, your brick, you're probably not going to get much more than 2 failures. But if you have more free space, it'll use that and give you better resiliency. Here's the thing, and this is as of Extreme IO OS 2.4. So by the time, whenever you listen to this, it may have changed. So confirm this with EMC or the release notes for the code level you're running. XDP does N+2 protection, but as of 2.4, you cannot pull 2 hard drives or 2 SSDs at one time. The protection is there, but the process to do a dual failure rebuild is not. So keep that in mind. Hopefully by the time you listen to this, that'll be changed and you can pull 2 drives and let them rebuild and then pull 2 more and get up to your 5. But just something to keep in mind. Performance is sustained even during failure situations. That's very nice because if you've ever had a RAID 5 or 6 set have a failure, you'll know that you will sometimes run into performance issues as it's doing rebuilds or as it's in a failure situation. XDP doesn't have that issue. So again, way better than traditional RAID. Garbage collection. We talked about this earlier in an earlier lesson, but bottom line is, and this is something that comes up, but bottom line is that SSDs like these here want to write in 4K chunks. So the SSDs in the Extreme want 4K chunks. If for some reason it writes a 2K chunk, it then has half a cell empty. And to be able to write to the rest of that cell, it can't just write another 2K. Just due to the way Flash is made, you get one write across the cell. So it actually has to read the 2K, clear the cell, and write 4K back down. If you do that, as data is coming in, it causes a performance penalty. So most systems do some form of garbage collection. That'll go back and reorganize the space on the SSDs to create as many free stripes, as we call them, or free cells as we possibly can get. And Extreme IO always wants to write to a free cell if at all possible. Extreme IO does what we call drive level garbage collection, in that it lets the controller on the drives do it. So each SSD has a little chip that's the controller, handles all brains of the operation for that solid state disk, and the controller handles the garbage collection. This is different than some systems that use system level garbage collection. Pure and Cisco Invicta do system level. I'm not going to get into the which one is better because it all depends on who you ask, and it really does depend on the implementation. But system level basically means that the controllers have a process that goes and does garbage collection instead of letting the drives handle it. Some people will argue that system level takes resources from the controllers and causes bursts of I/O that will impact performance. Some people say it's more efficient, whatever. But the idea is that on the extreme I/O, they feel that drive level keeps them from having periods of this heavy garbage collection, which impacts performance. And when you'll see that impact is when the array is getting full. At 30%, 40% full capacity, you're not going to notice it because there's going to be enough space out there for things to land on empty stripes. But when you're at 80% or 90%, that's when things like garbage collection can become really important and can cause problems with I/O. So if you're doing a test of arrays, that's why I suggest you almost fill them up to like 80 or 90% and then start beating on them and see what happens. Has full VAI support for VMware. VAI stands for VMware vSphere Storage APIs Array Integration. You'll see why we call it VAI. Bottom line is it offloads work to the array instead of your vSphere host, and it's a perfect match for Extreme IO's dedupe with the metadata content engine. So back in the day when we wanted to clone a virtual machine on VMware, the host would go to the array and say, give me all the bytes that make up that file over there, and it would be sent to the host, and the host would turn right around, hand it back to the array and say, write these bytes out to this new file here. Very inefficient. The array would have to both read all the data in and write it back down. It'd have to send it over the storage fabric. The host would have to get involved. So we came up with VAI, which basically said the host would go, hey, copy these blocks of data from here to there and let me know when you're done. So the array would go and start copying all that data and then tell it when it was done. It was efficient because it kept the host out of it, didn't send all the data across the storage fabric, and it kept some load off of the storage array because it wasn't actually sending and receiving data. It was doing an internal copy. So things were better. But Extreme IO, we can go even further than that. So Extreme IO, if you remember, is just basically when it does dedupe, it does a metadata update. So if it sees data that it's already seen before, it just adds additional pointers to the metadata table. Well, if I tell Extreme IO to clone a VM, what do you think it's going to do? Well, it knows it's already seen all this data, so it's just a metadata update. Very simple and very easy and very quick and really almost zero load on the storage array. And it's much faster than cloning data because the Extreme IO isn't actually even going to copy that data from one set of cells on SSDs to another set. It is simply just an in-memory metadata operation.